Brazil is a federal republic where the government is run by the three classic branches of power: the legislative, the executive, and the judiciary. The Chamber of Deputies refers to the house of the legislative power that represents the people in making laws and overseeing the acts of the executive. To do so, the deputies engage in discussions, conversations, and negotiations that are formally taking place in the committees and in the main plenary of the House during the official sittings. The legislative power is also referred to as the Parliament. This term comes from the ancient French parlement, from parler, which means to speak, to talk. In this way, the speeches are the deputies' weapons to convincing the peers into passing or rejecting a bill, or to start an inquiry to the executive branch. Thus, the deputies' speeches carry the constitutional force of decisions of the legislature. They are considered as official documents, making it mandatory to record them reliably. Along the majority of the last century, when audio recording was inexistent or unfeasible for the scale required by the Chamber of Deputies, only the shorthand technique was used for transcribing and recording the speeches. From 1970, the deputies' speeches started to be collected in the form of voice recordings, which provide an alternative avenue for transcribing and archiving them. An automatic voice recognition system can be of great value in the support of these tasks. With such a system, it is possible to perform speaker identification, speaker diarization, which is to segment the digital speech files by the different speakers, and the speech-to-text, which is to transcribe the speeches to digital texts. An automatic speaker recognition system can help the shorthand department in its task and can allow the publication of the speeches faster and more reliably. Speaker identification is the target of this project, and it is the first step of a program that will benefit both the Chamber of Deputies and the Brazilian democracy. Now that you saw the context of speaker recognition system development, let's take a look at some of the project details. First, we'll take a look at the stakeholders' benefits, then the development approach, assess the work done, and the next improvement on applying AI on the audio data of the Brazilian House of Representatives. The primary benefited will be the shorthand personnel, as they have to transcribe up to 1,000 speeches per month. They take from 5 to 8 business days to finish the transcribing of one sitting. But the project will also benefit the live participants of the sittings and the Chamber of Deputies Secretary of Communication. The goal of the project was to prototype a solution to allow the live identification of the deputy making a speech at the main plenary. The scope of the project was restricted to performing the necessary audio preprocessing and building and training a model to identify the speaker. Having defined the scope, the project started by obtaining an initial and usable dataset to allow the start of modeling. However, more data is still being obtained to improve training. Also at the beginning of the project, a research for an appropriate audio recognition architecture was made. The deep speaker model was chosen since it reported acceptable outcomes. A critical review of this model was delivered in September. Then, the project moved to development stage. A prototype model was delivered in October. The implemented model was trained and tuned, and its outcomes assessed and reported to the client. The remaining activities have been addressed. However, they still need to be finished and documented. Deep Speaker innovated in the speaker recognition task. While the traditional approach involves manual audio feature engineering to generate representations of the speakers, Deep Speaker uses neural networks to automatically generate representations of the audio. The embeddings generated by artificial intelligence proved to perform better than the traditional approach. While the traditional approach reached an accuracy of around 52% on the speaker recognition task in Mandarin, DeepSpeaker Best model presented an accuracy of more than 90% and a much higher resilience to time span. The first task in the development was to do the audio preprocessing. The speech capturing and segmentation were performed by the Chamber of Deputies. They provided each audio file with the speech of a single deputy. The client provided 272 speeches from 219 different deputies, summing up to 14 hours of speeches. Then, voice activity detection, or VAD, was performed on the speeches. This preprocessing technique consists of finding and removing the silent parts of the speech as they are useless for the speaker recognition task. After silence removal, the speeches become shorter. The initial 14 hours of speeches was reduced to 9 hours and 50 minutes. The next step was to extract spectrograms from the speeches. But what are spectrograms? Spectrograms are two-dimensional representations of pieces of audio, where a number of different frequencies are represented on the y-axis, time slices are represented on the x-axis, and the colors represent the amplitude of each frequency over the time frames. The problem becomes similar to image classification. To get the spectrograms, we pick up audio windows of around 2 seconds. You use overlapping time framing to capture the transitions between the windows. The 9 hours and 50 minutes of non-silence speeches become around 35,000 spectrograms, summing up to 1.1 gigabyte of data. Then, focus moved to model building. The model was developed in Python using the PyTorch package. A simpler model was used as a baseline. The target model was coded based on the ResNet model from the Torch Vision package. Fellow colleague Márcio Fonseca helped with this task. The final model was named CD Speaker Identifier. Moving on, the training was a matter of adjusting hyperparameters and waiting overnight computations. It took, on average, 6 epochs for the training to converge and provide a validation accuracy of 97%. Further tests are needed to confirm this accuracy. CD Speaker Identifier presented outcomes far better than the baseline model. Assessing the work. The first reflections are over the differences between DeepSpeaker and CD Speaker Identifier. The first main difference is the level of the embeddings. CD Speaker Identifier uses relatively long speeches to extract multiple spectrograms and map them all to one deputy. From shorter utterances, DeepSpeaker generates fewer spectrograms and converts them to an embedding that represents the orator. One speaker will have multiple embeddings from his/her multiple utterances. The difference of approach is partially explained due to the characteristics of the available data. While this project had fewer and longer speeches, DeepSpeaker used shorter and far more utterances. For instance, while this project had 272 speech from 219 deputies, DeepSpeaker used 12 million utterances from 250,000 speakers to train its models. Another main difference was the loss function. CD Speaker Identifier used a softmax cross-entropy function in the classification layer. DeepSpeaker used softmax for pre-training and triplet loss for improving accuracy. CD Speaker Identifier uses a particular inference approach. It has to consider the frame-level embeddings and the peculiarity that the speaker must be identified in the beginning of his/her speech. To infer the deputy speaking, the first 3 seconds of audio will go through the semi-preprocessing techniques used to extract spectrograms. The spectrograms will then feed the trained model, which will output the classification for each of them. In a softmax fashion, the majority classification will be assumed to be the deputy with the word. Considering possible improvements, as any deep learning system, more data, the better. The training data shall at least cover the 513 deputies. Currently, only 219 are known by the model. Another approach would be to extract 128 frequencies from the voices of the speakers. This would provide more information for the model to learn from. The drawback is that this approach would require even more input data, more computational power, and it would be slower to train. Another possibility is to use vocal separation preprocessing to isolate the voice of the speakers. Despite the different scenarios, it should be interesting to use original deep speaker features such as utterance level embeddings and triplet loss to assess if they would improve accuracy for the Chamber of Deputies use cases. Finally, this project recommends the Chamber of Deputies to update the audio capturing system to send the audio stream for preprocessing and then to feed the inference model. The systems fed by the deputies' name information will also have to be updated. The Chamber of Deputies can also thrive in other domains of speaker recognition. This project implements the identification capability. Speaker diarization can be used to annotate audio files, including old ones, and make research on the Chamber of Deputies audio archive easier and more precise. Speaker verification can be used as an alternative authentication level for the voting system or for conceding access to restricted facilities. On a higher domain of artificial intelligence for audio, speech recognition could be used to automatically transform speech to text to ease shorthand department job even more. Language recognition would be a first step to performing live translations on Mercosur Parliament sittings. Well, this is pretty much my journey on developing CD Speaker Identifier prototype for the Chamber of Deputies. At last, I'd like to thank the collaborators of this project. Eduardo Melo, the first point of contact, Michael Onishi, the manager who later embraced the project, fellow friend and source of inspiration for engaging in data science, Márcio Fonseca, Iago Teixeira for the support on acquiring data, and my mentor at UTS, Alex Scriven, for the guidance in this journey.